Okay, so we're looking at page 6, number 5. I'm going to take this one from scratch. Find the area outside of r equals 4 sine theta and inside of 7 cosine theta in the first quadrant, so specifically in the first quadrant. All right, so we know the purple one is the 4 sine theta. And at this point, that's more experience than anything else. And the black one is 7 cosine theta. So if we're going to be able to figure out the part of the graph that is outside of the purple, but inside of the black, but in the first quadrant, then one thing that we're going to need to do most likely is find an integral, right? But there is a little wiggle room that we could use because we have this part of the northern hemisphere of that Death Star over there that that's really just a semicircle, right? The diameter is 7, which means the radius is 7/2. Okay, so I can say that the area of that semicircle is going to be pi r squared over 2, so 1/2 pi r squared. So 1/2 pi times 7/2 squared, 1/2 pi times 49 quarters is going to be 49 pi over 8. All right, so we got that part of it. In order to figure out the remaining, well, not really the remaining, but the piece that needs to be excluded from that, we would need to figure out the area of this guy over here. All right. So what I'm going to do, or what I'm going to need to do, or will need to do, is figure out a couple of things. One, what that intersection is right there. Because we don't have symmetry that we can rely upon here. So what we're going to have to do, I'm going to bring this in, is we're going to have to figure out this area. Oh, that looks terrible. And then once we've done that, we'll have to shift over and figure out the area the rest of the way. Okay, and then once we get that sum total, we can subtract it off that 49 pi over 8 or whatever it was. All right, so let's start off, excuse me, we'll start off finding the intersection between those two polar graphs. So we're looking at, and we can assume one of them's at the pole, so that's easy enough. All right, so, well, we might as well do that. So the intersections, almost went O when I should have went I. You'd be at the pole. That's where r is equal to 0. So I could set each of my equations equal to 0. So I have 0 equals 4 sine of theta. The other one's 7 cosine, right? And 0 equals 7 cosine of theta. All right, so sine of theta equals 0 when, well, in a variety of circumstances, but the one that I would imagine we're interested in would be when theta is equal, or a couple of them, would be theta equal to 0, theta equal to pi, but if we're only focused on the first quadrant, we may not even care about the pi, but I'll write it anyway. 0, pi, and 2 pi, technically we can get all of those in. But we know our domain only goes as far as pi, but that gives us one full turn around the circle, right? The purple circle, all right? I'll even make this purple. All right, so if I were to say only go to 0 to 0, it doesn't give me anything because it hasn't left the pole. All right, so if I smidge out from there, let's say I go 0.01, see a little bit of a purple blob shows up there. It's kind of hard to see. It's coming out there a little bit, but it's there. All right, so it's working its way out from the pole. So we know there's something there. And if I get a little crazier and I go to like pi over 6, it's working its way out. And maybe pi over 3, and pi over 2, that's the half circle. Maybe that's all we care about. Definitely a little bit more than whatever the intersection is between the two, right, which we'll have to figure out in a second. All right, so for the other one, we're looking at cosine of theta equal to 0. That happens in a variety of circumstances. Pi over 2, 3 pi over 2, and so on. 5 pi over 2, negative pi over 2 if you want. But let's just kind of focus on the 0 to pi over 2 interval. Not pi 2, pi over 2. All right, that gives us a semicircle, so that's good. It's keeping it in the first quadrant. So if we go to pi over 2 in both cases, we're fine. But we know, or at least it looks like, this one hits the pole. So it's at the, because that's really the ultimate objective here, is to determine when it hits the pole. So let's say I start off at pi over 3. Well, not even pi over 3. Let's say pi over 12 a little bit. Pi over 6, a little bit more. A little bit more. It isn't until pi over 2 happens that we hit the pole. So we know that when theta is equal to 0, the sine function's at the pole. And when theta is equal to pi over 2, the cosine function's at the pole. Now we'll figure out where they intersect with each other than that one particular location. All right, we're gonna work these two graphs independently, but it's worth finding out this information. All right, so for sine theta, if anything, it's good practice. 7 cosine theta. I want to solve for theta, ideally, but these aren't clean unit circle values. Otherwise, we'd have some sort of recognizable intersection, like well, it kind of looks like it could be at pi over 3, but not quite close enough. All right. So I'm going to divide out the 4. Sine of theta is equal to 7 quarters cosine theta. Now, there's a couple of different strategies you can use. One would be to create a graph. Right, in the last video that I posted, that's actually what I did, and we get a decimal answer. But if you want to do it more analytically, what we could do is divide both sides by cosine. I gotta use my line draw tool here. My line game is dreadful. You don't need me to tell you that. All right, so I can divide both sides by cosine of theta, and what that does is it takes our sine and makes it into a tangent. Sine divided by cosine is tangent of theta. Cosines would cancel on this side. We're not losing a variable, we're just merging it with another. All right, so 7 over 4. And then I could say that theta is equal to the inverse tangent of 7 over 4. All right, and then I can just kind of rough that out. Inverse tangent, 7 over 4. Approximately 1.0517 radians. So that's information. We might want to just leave it as the inverse tangent though. It's cleaner. No rounding involved. Get a more exact answer. All right. A little bit of variation due to rounding is okay, but if you get too far away from it, we might have a problem. All right. So what I would want to do here is first make sure that we didn't screw this up. But what I really want to do is come up with a true graph. All right. So what I'm gonna do is I'm gonna duplicate what I have. All right. I'm gonna duplicate all that stuff. I'm gonna see if this will work. It hasn't worked yet, so let me try it. C equals, and let me C be equal to that. And then for my domains, I want to have the ordinary sine and cosine functions, the polar graphs. I get an extra inverse trig. Oh, I don't know where that came from. I want the sine function to go from 0 to c. Will it work? Well, it didn't give me an error message, so that's a win. All right, where c is defined, I'm getting a little scroll hat here. I'm going to move this up to right above that. 0 is where the graph started, and c is where I want it to end. It looks like nothing changed, but we have overlapping graphs, so that part should be okay. Then for the other one, we know that it gets back to the pole once it hits pi over 2. I want it to start at c. All right, so this is the big moment. I'm going to turn these graphs off and see if I got what I needed. And it looks like I do. And I got that little leaf. All right, so what that's telling me, or what it's confirming for me, is that I actually found, or we found, the necessary bounds. We found the bounds. I can't stop myself sometimes. And so what we want to do, we'll focus on the purple first, is on the interval, and that's the sine function, of 0 to c. So c being the inverse tan, you could go with the decimal like I said, inverse tan of 7 over 4. We have 1/2 r squared d theta. All right, and with the r being 4 times the sine of theta. All right. Then for the other one, we have on the interval of inverse tan of 7 over 4 to pi over 2, 1/2 r squared d theta, with the r being the cosine function, the black, that's 7 cosine theta. We're going to add these two together. That's going to give us some result, which we would then subtract from this. All right. All right, because again, this little leaf here is the thing we don't want. All right, so, there's a little bit of work ahead of us, but it's still doable. All right, this, if you want to see how to handle a sine squared or a cosine squared integral, you can look at, I believe it's the next video. But here we'll just do it in Desmos because we're going to be at this for the rest of our lives if we go continue doing this by hand. So that's one of the reasons why I keep saying that you could use a decimal form instead of the inverse trig, because I knew we were going to go to the calculator at some point anyhow. So miscellaneous integral. Inverse tan, I have that stored in as c, so I'm going to make use of that. All right, so 0 to c. Open paren for the integrand. We have 1/2, so 1/2. 4 times the sine of theta. Back to trig, not stat, trig. 4 times the sine of theta squared. Close it up. D theta. All right, we can hang on to that, or we could just tack right onto it. I'm going to tack right onto it. Plus integral c, which is my inverse tan function. Again, you could put the decimal in if you want. Pi over 2, open paren for the integrand, 1/2, open paren for the 7 cosine of theta, close it up, square it, close it up, d theta. As long as you type it correctly, stand a good chance of not making a mistake. All right, so we got this decimal here, which is, I mean, if you want to start fiddling and seeing if it's some sort of multiple of pi, go for it, but I'm just going to write the whole thing. It's approximately 3.56614074971. So let me just smidge it over. All right, but if you really, really want to do it all in one shot, then, because we're going to take that and subtract it from the original function and go all the way back to the beginning. Make sure you get an open set of parens and closed set of parens, and type in your 49, I slipped, 49 pi divided by 8, and then right arrow over, and I accidentally hit the wrong thing, and throw a little subtraction symbol in there, and you'll have it. All right, so we would be doing, so therefore 49 pi over 8 minus, it's really going to be approximately 3.566. Result is going to be, everything's approximate, 15.676. All right, and that's the area of the semicircle excluding that little leaf, if that's what we're going to call it.